Okay, folks, welcome back. We got section 9.2 here, summation notation, and this course is called pre-calculus. So hopefully, some of the things we do have a relevancy to calculus. And in calculus AB, you'll only see this a little bit. You'll see it more in Calc BC, or at least needed to use it more in Calc BC, which is the equivalent of Calc 2 in college. So just a little bit we'll see in Calc 1. And then a lot in Calc 2, just to give you some background. Okay, so let's get started. If we're given a sequence using this notation, and that's the notation our textbook used in section 9.1 to define a sequence, where the index n goes from k to infinity, and the numbers m and p, so we're also given the numbers m and p such that k is less than or equal to m, which is less than or equal to p, then the following is true. So let's decode all of the symbols here in this statement. I'll first start off by saying that this big, strange symbol, that's the Greek letter sigma. Then I'm going to talk about this letter n right here. N is called our index or position. M is our lower limit. You may also call it the starting point. P is the upper limit, or where we finish. And now let's talk about everything we got here on the right hand side of the equal sign. A sub m is our first term. A sub p is our last term. And everything else, you should notice we have a plus, 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 plus. This is all a giant sum. Okay? So this indicates that we are taking the terms of a sequence and adding them up. That's where we get the word summation from. Okay, so a verbal description of this whole mess is the following. If a sub n is a sequence, then this notation here means the sum of the terms of the sequence a sub n from the first term, a sub m, to the last term, a sub p, where first and last are defined by our lower and upper limits. Okay, so that is the definition of the summation notation, what it means. Let's go ahead and do some example problems. So this first example we have here, I have to sum the sequence 3n plus 2 from n equals 1 to n equals 4. So I'm going to go ahead and write this one out and show you each of the steps. So my starting value is 1, so I'm going to do 3 times 1 plus 2. Then I go up, my index moves up to 2. 3 times 2 plus 2. My index then moves up to 3. 3 times 3 plus 2. And finally my index moves up to the upper limit, 4. 3 times 4 plus 2, and I stop there. So let's see what we get. That's going to be 5 plus, let's see, 6, 7, 8 plus 3 times 3 is 9 plus 2 plus 11, and then we get 12 plus 14. Okay, so I simply add up those integers and I get value 38. So this sum of terms for 3n plus 2 is 38. Pretty easy. Okay, so what I'm going to do now is I'm going to grip it and rip it through the next two because they're very similar. Okay, that was a quick run through parts B and C. Now let's look at D. With part D, there's a couple things here that may look a little strange to you. First of all, let's talk about the index. This uses J as the index in our sequence, and some students are like always confused by that. Oh my gosh, we never see J. Well, it's just like N was in the previous problem, or K in part B. So it's just the index. Don't be too alarmed by that. The second thing I'd like to point out is this symbol right here, which might be new to some of you. Exclamation point. So this symbol here, 5 exclamation point, it does not mean 5. What it means is 5 factorial. So let me talk to you about what 5 factorial represents. 5 factorial is equal to 5 times 4 times 3 times 2 times 1. So it's the integer 5 times every number below it, every whole number below it until you get to 1. So 5 factorial is actually 120. And if you are so inclined, you can find the factorial button buried in your calculator somewhere. That function is going to be built into your calculator. 4 factorial is going to give me 4 times 3 times 2 times 1, or 24. 3 factorial, these get easier as we go down. 3 times 2 times 1, which is 6. And finally 2 factorial, which is 2 times 1, or 2. Okay, so that's what that notation factorial represents. If you've been, you'll encounter that in counting problems and probability problems. So anyway, let's go ahead and write out this sequence now that we know what all these factorial things represent. All right, folks, the answer to part D is 25. And one of the things that I did here is, I hope you notice I factored out, I have that 5 factorial, or 120, that's in every term. So I factored it out just so I had a little less writing to do. And then, the sum of those 3 fractions right there is 5 over 24. I was able to kind of think through that mentally with a common denominator of 24. You got to multiply each of these fractions by 2 over 2. You may not have been able to do that, but that's where that number comes from. And then, in terms of simplifying to get 25, I know that 120 divided by 24 is 5 times 5, and my numerator gives me 25. That's great. Let's move on. This problem, part E, presents a significant challenge. Take a look at this. I'm going to be adding up a sequence from 1 to 100. I got 100 terms to add up. That seems ridiculous. That's so ridiculous, in fact, that I'd like to write this. Whoa. Okay, there's got to be a trick to this. There's no way that I could expect a student to reliably add up 100 terms. So let's go ahead and see what happens in this one. So I have 2 times, I'm just going to go ahead, I'm not going to show you the arithmetic to get each term. I'm going to kind of do that just to show you I'm going to show you the term. So I have 2 times 1, it's 2, plus 1 is 3. So my first term is 3. My second term is 2 times 2, which is 4, plus 1 gives me 5. My third term is going to be 2 times 3, 6, plus 1 gives me 7. Okay. Now, I can see that that is a arithmetic sequence that's increasing by 2. So let's think about the 99th term. I'm going to do 2 times 99, that's 198, plus 1, which gives me 199. My final term is going to be 2 times 100 plus 1, or 201. So let's take a look at this. I wonder if there's some kind of a pattern that we could see here. Well, let's just consider the following. What is 3 plus 201? Pretty sure if I add those two numbers up, I get 204. I wonder what happens if I add the second term and the second to last term. Let's see, 199 plus 5. Hey, that's also 204. This pattern is going to repeat. If I add the first term to the last term and then I work my way towards the center, I'm going to get a sum of 204. Now, this sequence has 100 terms in it. If I do 100 divided by 2, because that's how many of the terms I'm including in each sum, that's 50 pairs. So this pattern of 204 has 50 pairs. So the sum of this sequence is going to be 50, number of pairs, times 204. And that gives me a final answer of 10,200. So that's a pretty nifty way to add up a sequence of terms, especially when there's a whole bunch of them. We don't have to do it manually if we look for a pattern there. Okay, let's move on to part F. Okay, for parts F and G, we're going to use a similar approach to what we did in part E. We have even more terms to add this time. It's 120, but let's see if we can pick up on any patterns that will simplify our summation. So with this one, I'm going to start by looking at just the first couple terms. So I have -1 to the first power plus -1 to the second power plus -1 to the third power, and then I'm going to continue up and go -1 to the 119th plus -1 to the 120th. Let's go ahead and simplify these before we look for any patterns. -1 to the first power is -1. -1 squared is +1, so this is going to be +1. And then -1 cubed, that's -1 again. So this, it looks like this is going to alternate back and forth between +1 and -1. 119 is an odd number. The odd exponents gave me a negative output, so this is going to be -1. And then 120 is an even number, that's going to turn back into +1. So let's take a look at what we got. If we take our first term and our last term and add those together, we get 0. Go second term to second to last term, we get 0 again. So when you add these pairs, we get 0. We have 60 of them because if we take 120, the total number of terms in the sequence, and we divide by 2, total number of terms in the sequence, 120 divided by 2 gives us 60 pairs that add to 0. Well, we know any number of times we add 0 to itself, we just get a result of 0. And I'm going to let you look at example G on your own. Example G is going to give you the same result. Example G also adds up to 0. It has that same alternating pattern back and forth between -1 and +1, except with this guy, n-1 is the exponent, the sequence actually starts at +1, then alternates to -1. So it's a slightly different sequence than the one in part F, but the result is the same. Okay, that's it for this video. Stay tuned for part 2. That'll coincide with page 2.